4, 1, 4, 2, and 4, 4. 4, 4 we kind of broke into two pieces. There was the horizontally fired projectile, and there was at an angle. Right? Horizontally fired and at an angle. In 4, 1 and 4, 2, we talked about the fact that a vector is anything that has a magnitude and a direction. A magnitude and a direction. So for example, if I said to you, ask if they close the door. That's fine. It's okay. Okay. For example, we could say, I walked 5 feet. Or I could say, I walked 5 feet at 20 degrees northeast. There's a big difference between those two things. 5 feet is just the magnitude of the vector. Magnitude. The direction comes from the angle. You know the kind of example you're going to expect. All of the vector problems we did, either you did them graphically and showed on a grid where you connected the actual lines themselves, vectors, and then found the resultant. Or you did it algebraically. You're going to have both of those. I'll give you a hint right now. You will absolutely have one of each. Now, that doesn't mean that's the only problem with vectors. I could say, a person walked 5 blocks north, then they walked 12 blocks west. If they walked a straight line, what would the overall distance be in blocks? I know it's not blocks, but 5, 12. The straight line would be the hypotenuse. So in that case, it's like a right triangle. So vectors apply themselves in a lot of ways. In addition, they also apply themselves when we find final velocity of an object when it's either hitting the ground or somewhere along the way. We have to put Vx and Vy back together with vectors. Or when we determine V bar x and Viy, we use sine and cosine, which are vector components. So this plays a big role on this test. Let's look quickly at a graphical example. So if this is vector A, and this is vector B, and I ask you to sum together vector A and B, what we're thinking again is the model of tip to tail every time. So let's start with vector A, which is in black here. Oops. Vector A. And to that we'll add vector B. And the way we draw this is we start by redrawing vector A on its own. You can draw it right from where it is, but I'm going to show you from its own. And then we draw vector B directly from that location. The final result of the sum of these two vectors is what we've been calling the resultant the whole time. Okay, the resultant. And the goal, if I have a grid line, right, if I'm doing this on a graph, all I got to do is make the triangle, right? I just have to make the triangle for the vector r at this point. So I take the vector r and I literally make a nice right triangle with it. And if I can figure out those distances, rx and ry, I can easily find out the actual value of the vector r. So remember that what we're doing is we're adding pieces together. We're adding pieces together. So let's say that this first vector goes up 3, well, we have lines here actually so we can use them, but let's say it goes up 3 units up, and it goes over 2 units. And the second vector only goes to the right, let's say, 4.5 units. There's no up or down, it's only east in this case. I know it's not drawn perfectly, but say it's east. So if I were to figure out Rx, to look for Rx, I would see that the first vector went to the right 2, which is this, and then it went over another 4.5. So Rx is going to be 6.5 in this diagram. So using the graphical approach, we can literally count boxes, right? Almost like slope. Remember slope? When slope was 2/3, you go up 2 over 3. Well, the same concept here, if you're doing this on a graph, which you would be doing it on a graph for a graphical analysis, this Rx would be the sum of 2 and 4.5. And Ry would simply be 3. Okay, again, the x vector component of the first one. The second one is all in the x direction. And then the first one has the y component is 3. That's on the far right. Now the last piece is to recognize that you're always also going to be asked to find a direction when you look for a vector. So the angle theta is always the angle that your vector makes with the nearest x-axis. The nearest x-axis. If my resultant vector went like this to the left, then my angle theta is this piece right here. If my resultant vector was my arm and went left instead, the angle theta is measured to the nearest x-axis, not all the way back to the positive x-axis. So in this case, that's what theta would be. How do we find theta? This is opposite, this is adjacent. Use the tangent function. The tangent of theta equals 3 over 6.5. Tangent inverse gives you theta. Tangent inverse gives you theta.
How did you get the blue number 3? Would you have calculated
Yes,
it?
and so I'm going through the graphical approach right
Okay.
now, where you would be just physically counting the boxes on a graph.
Oh, okay.
The vector would be drawn on a grid, and you would be able to see how far it moves.
Okay.
So graphical is the first way to think about this.
And
Panaccio.
how do you find theta?
How do you find theta? So if I look at theta, I take a look and I see that this is opposite and this is adjacent. So opposite over adjacent is the tangent function. So the tangent of theta equals opposite, which is 3, over the adjacent, which is 6.5. So to find theta, we'll do the tangent inverse of that ratio. Okay? That's a 3. 3 over 6.5. Okay? Chris?
Only time we're using tan inverse is
Theta.
for these.
Yeah, for
These
theta.
types of problems, just for like finding that direction, right?
Yep. Absolutely. If you're like hypothetically finding theta for a projectile motion problem, you probably use cosine inverse or sine inverse because the vector components involve sine and cosine. Remember that? Okay. Only when you're finding theta for an actual resultant do you use tangent.
Wait, so this is graphically?
This is the graphical approach to this. Correct. This is given on a grid that this goes up 3 boxes, this goes over 2 boxes, this goes over 4.5 boxes. So you're physically seeing it on a grid. Okay. If we're doing this algebraically, I recommended that you use a table because the table is an organized tool for that. So let's see a quick look at that. And I'm really just going to approach this the same way I did in class, so I'm not changing anything. So hopefully if it was a little confusing the first time, after doing enough problems and practice over the last 2.5 weeks or so, we have a little bit more confidence in our work here. So let's start with an object that's moving, let's say at a 30-degree angle. And let's say that it moves a distance of 5 miles. And then it moves east a distance of 6 miles. And then south a distance of 2.5 miles. Oh, that's not reasonable. 7.5 miles. I'm going to try and draw it somewhat to scale. Let's draw the resultant now. From A to B with a straight line. Okay, so the resultant here is in blue. And for this kind of a problem, we have to recognize that we have pieces of the vectors that we have to consider. So when I'm looking at this problem, I want you to be thinking of it visually. I want you to think of this graphically as you're doing it. 2 of these vectors do not involve components. 1 vector does involve finding the components. How do we know which one is which? When do we use components of a vector? If it's at an angle. So the 6-mile length and the 7.5-mile length are not at angles. But what I mean by angles opposite or angles other than the x and y axis, right? Besides vertical and horizontal. Anything that's vertical or horizontal is only the x or only the y. It's one of the two. So those 2 second vectors are not very difficult at all. In my table, I give a 0 for one value and the other one gets a number. But here, I need to break this into x and y. And think of its triangle. Right? X and y. So again, I'm thinking of this first one like this in red as x and y. So I go to my table and I say, well, each of these vectors has components to it. Sometimes they're 0, sometimes they're not. The first vector is a 5-mile length. So I know that there's going to be a 5 in these cases. The angle is 30 degrees. If I want the x component, which trig function do I multiply it by? Tan. Cos. Careful. It's all right. We just did tan. That's what you're thinking. If I want the y component? Sine. And what is theta in this case? It's 30 degrees. So these values here are 30 degrees. That's my angle that I'm using. Now, in the next part, some students I've noticed when they've done their work, I've looked at some of your homeworks here, a lot of you, or not a lot, but some of you have used 90 degrees or 0 degrees here. And that's okay, you can do that, because technically the 6-mile one is at 0 degrees. See the 6-mile one here? What's the angle between here and here? 0 degrees. What's the angle between here and this? That would be 90 degrees. So if you want to use this, it's okay, but you don't need angles when it's in the x and y. 6 miles is only in what direction? Everyone. Yeah, horizontal, x. Is it positive x or negative x? So we know for the second vector it's going to be a positive 6 and nothing for the y. Why were these first two both positive here? Why was 5 cos 30 and 5 sine 30 both positive? Because they could be negative in certain circumstances. Why are they both positive here? Luce?
Because it's going up.
And?
It's going right.
Very good. Right is positive in the x, up is positive in the y. The last vector, what am I going to write for it? What am I going to write for the last vector? Bridge.
0 for the x and 7.5 for the y.
No, negative.
Or negative.
There you go. It's all right. See? Your classmates are a little critical of you. That's fine. No, I'm kidding. Good, good. Correct each other. That's right. Negative 7.5 for the y. So the resultant itself is this last column here. And this value you get here is Rx. And this value is Ry. And really, if you want to see in the diagram, because I know some of you are still like, ooh, I don't really understand it fully, let's show what that is in the diagram. I'll use dashed black lines here. That's Rx and Ry right there. It's just like the graphical method. It's actually the same as the graphical method. We're just using values in a little bit of trig to get the values of Rx and Ry. Of Rx and Ry. Okay, this is Rx here, the base of the triangle, and Ry is the height of the triangle. And we literally add straight across. Add straight across. Once you get Rx and Ry, you can go to the exact same method from graphical. Pythagorean theorem gives you r, and the tangent inverse gives you theta. The tangent inverse gives you theta. What do I get for those values? Do we have numbers? If anyone has it already? We don't really need to do it. It's fine. We can move on to the projectile motion stuff. The process is what's important right now. Where's theta in this diagram, by the way? Where's theta going to be? You have to speak exactly where it should be. Go ahead. How are you going to describe it?
Isn't it in between the resultant and the x-axis?
In this case, though, what's the x-axis? Is it above it? Is it below it? Where is it?
It's the rx.
It's not the Rx. It is the same angle, but that's not the one we're looking at, really.
Opposite. It's like the opposite ulterior angle from
from that little spot. See where it is, Daniel? So yeah, it is this value. You're right. You can use this one. That's okay. But what I want you to know is this. It's going to the right and then down, which is south of east. South of east. That's east. This is south of east. And how do I know the answer is going to be south of east? Take a look at my numbers. Rx is definitely going to be positive. And I'm pretty sure Ry will be negative 5. Is that what Ry is?
Yeah.
Negative 5. Okay, and Rx will be what?
10.3.
10.3. So the fact that this is a negative resultant for Ry means that this person, after doing all of this movement, really just went east and then south of that. So your answer for this problem, already we know, will be some number at some angle southeast. That number will be measured in miles, and that second number will be in degrees. I'm putting the answer in the top right. Okay? Take the square of these, square them individually, sum them together, take the square root, that becomes this number, and then do the tangent inverse of Ry over Rx, which will be tan inverse of 5 over 10.3, and that'll give you your angle theta. Remember, when you do the tangent inverse, you don't have to worry about negative and positive. The idea is that southeast already takes care of the fact that it's going to be negative in the y direction. So again, when you do tangent inverse, use 5 over 10.3, and that's why I put absolute value around that when we did in class the first time. Absolute value is useful.
Wait, how do you know it's 5 over 10.3? Like, where do you get that from?
I just added across.
No, I know that, but I'm saying, like, is there like a rule?
Yeah, because remember, this is your angle here. This is your angle here, right? The same. Opposite over adjacent is tangent. So it's going to be this over this. And it always turns out to be Ry over Rx. So that's something you might have picked up on over time. You may not have yet. But it always turns out to be tangent inverse of Ry over Rx. Lucy.
So the SE stands for south of east?
South of east is what it really means, yeah?
So we can just measure it?
Sure, but technically this is east, and you go south of that, and that's your directional. That's why I put the word of in there. And your textbook says the same thing. It's actually smart to recognize that that's what it actually means. Because you could, and you know, I've worked it from other textbooks outside of school for like physics, AP exam, test prep with like kids outside of Loyola. Some books do like weird stuff and say like east of north, east of south, and that's fine. It's acceptable also, it is. But why change up the system that we're using that works? And this is a good system to use. So we could have said technically east of south, but then our answer would be the complement of that angle. So if this was 20, Lucy, this would be 70 degrees east of south. Instead, we're saying 20 degrees south of east,
Okay.
because they add up to 90 in each quadrant. Chris?
Wait, so how do we know how to get that angle out of?
Look at your triangle right here. This is 5. This is 10.3. You're looking for theta. The theta is really that angle right there. So it's just opposite over adjacent. Tangent. Look at your notes again. Tangent. Tangent ratio always works for this every time.
Could you calculate it without drawing R, Y, and Rx and using the inside one, or no? Or should you draw?
Yeah, because this is also Rx, and this is also like Ry.
So would Rx be 10.3 still, and then RY would still be -5?
Yeah.
Okay.
And when you do the tangent ratio, though, use positive.
Okay.
If you don't, it'll just give you a negative number, but you're using the positive angle because south already indicates that it's down.
Okay.
Okay? I do want to move on to projectile motion and just have a minute or a couple of minutes at least to ask you if you have questions on it. We talked about the main 5, right? There are 5 types of problems that we've really looked into at this point. Now, remember, one problem in part A could say, find the max height. And then part B might say, find the total time of flight. So it could be putting 2 of those problems together. But there are really 5 main things that we talked about. Launching from ground to ground, launching up, launching down. We talked about the max height problem itself, firing horizontally, that problem, and then the problem where we find the impact speed. That was another one, or the speed at any given moment along the way. So what do you want to work on is my question at this point.
Impact speed.
Impact speed problem or speed along the way? Probably one of the hardest ones that we've done, so let's do that. So let's say an object is fired with a VI of 20 meters per second east. 20 meters per second east. It's fired from a cliff, and the cliff has a height of 15 meters above ground. Cliff has a height 15 meters above ground. And our question is going to be, let's say, find the impact speed, or I don't want to pick a time arbitrarily. Let's find the impact speed when this object hits the ground. Impact speed we're looking for is final time lead. Okay, so we can do, I'm trying to think if I have to give you more information or not. I think we have enough information right now. So based on the givens that we have here, we're looking for impact speed when it hits the ground. We go to our XY direction right away. This object is fired east from the cliff. So tell me about the velocities here. What's V bar x and what's VIY? If it's fired east, Bridge?
VIX would be 20 meters per second. VIY would be 0.
Very good, Bridge. This is the horizontally fired problem I'm putting together with where it lands on the ground. Remember, this is how we started section 4.4. A lot of people are forgetting this kind of problem. We've been doing so much with problems at an angle lately that you forget that this is the simpler version. If it's fired horizontally, all the velocity is in the x. This is 0 always. Now, we want to...
Wait, so VIY is always 0 when it's launched horizontally?
Absolutely, always. Because which way is the velocity initially? It's horizontally. That's the whole concept behind this. And the key word here was east. If it's fired east, it means the projectile is launched with a vector like that. And then it starts to fall. As it starts to fall, its y velocity becomes what?
Greater.
And greater in the negative direction. So we know that our answer is going to have some number that's not 0. So our goal is going to be, can we figure out what this value is in the y direction? Why don't I care about the x direction for this problem, or at least right now? Danny?
Stays the same.
Good. The x velocity is always constant, hence the bar above it. And that's always 0. So I'm going to leave the x alone for a minute and move to the y direction. Can we figure out, is there a formula we can utilize to help us find VFY? Well, what else do we have? What else do we have in the y?
Wait, but why don't you use why don't you use like the cosine of 20?
Because it's not at an angle. Different problem, Alex. Remember, when it's not at an angle, it's only fired. You can use cosine 0 here because the angle is 0, but the cosine of 0 is 1. So this becomes 20.
Okay.
You could write here 20 sine of 0, but the sine of 0 is 0, which makes that go to 0. So if you want to use an angle for the horizontally fired problem, you can, but the angle is always 0, which puts all the velocity in the x and none of it in the y. Okay, so the angle works for this technically, Alex, as long as you remember it's 0 degree. Panaccia.
I have a question.
Yeah?
Is it the solution also 0 for like
Always, because we don't assume there's any wind or air resistance. Okay, that's the reason for it. What's the...
Sorry. Will we have anything with air resistance?
Mathematically, no. Would you have to maybe discuss? Absolutely. You should understand the concept behind it, but no, you would not have to do it mathematically. What's the last piece of information that we haven't written that we know that we need to use for the actual VFY?
Y equals -15.
Good. Y is -15 because you're falling down. So, what formula should I use to find VFY? And then I can put them all back together afterward once I have them both. Go.
You would use VF to the second equals 2AX. So then you would take out the VI because it's 0.
Well done. She already recognizes, and I'm going to use subscripts everywhere just to recognize that. She already recognizes that when VI is 0, this formula drops off, or this part of the formula drops off every time. And we've had that happen a couple times already, right? We've seen that happen with the VI, with VIT plus 1 FAT squared, with the free fall problem. So we solve for VFY. Plug in numbers at this point, please. It's the square root of 2 times A times Y. What would happen if you forgot to make Y negative? Take a look. What would happen if you forgot to make Y negative, Chris?
You get a negative in the
Radical.
in the radical.
You get negative under the radical. Can you have that right now? No. It's an imaginary answer. You'll talk more about that in math. It's not a real answer for a mechanics problem. It is used in engineering. Imaginary numbers use a lot in engineering. What does VFY become? What does VFY become, Emily?
17.2.
And Emily, can you be more specific than 17.2 meters? Even more than that. Something else. I'm putting you on the spot. No,
South.
careful. Why south?
Oh,
Stop. Why south? Yelling out directions.
because it's just going south.
What direction are we looking in right now? Are we looking in the X or the Y?
Direction.
The Y direction. Aren't we finding the Y velocity at the end? And which way was this object falling?
Down.
So it's negative. Remember, it's plus or minus. But we need to be rational thinkers and say, oh, it's definitely negative here. It's plus or minus, but yeah, Mr. Howell's right. It's negative because it's falling down. So the Y velocity at the end is negative 17.2. The X is always 20 in this problem, always. So if I want to find the overall velocity or the overall impact speed at the end of the problem, I need to put the pieces back together. The X velocity is shown like this. The Y velocity is shown like this. The overall velocity is the vector from start to finish. That's what we're trying to figure out right there. Our goal is to find VF in red. Okay? Again, I know 17.2 said it was negative, so it just means it's going down. So my vector at the end is going to be down and to the right. But if I ask you for impact speed, or if I ask you for the magnitude of the velocity, it means just give me this number. I'm not asking about the sign or the negative part, or the angle part. Okay, you're not asked for theta if it doesn't say give the velocity, or if it says find the velocity, you should give magnitude, direction. If it says find the speed, you just give magnitude. If it says find the magnitude of the velocity, you just give the magnitude. The theta value is not as important here. Okay, with the vector example, I'm going to have you find theta. I'll tell you now, for these speed problems, you're not going to ask you for the angle. So what I want is the final velocity of the object, putting these two pieces back together. And it's going to be a bigger number because it's moving with 20 to the right and 17.2 down. So it's going to be something larger than that, and that's why it's a hypotenuse in the triangle. Hypotenuse is the longest side. The answer is going to be larger. What do you got?
26.4 meters per second.
Okay, that sounds good. It sounds reasonable because I'm just looking at my numbers real quick, right? I know it's going to be greater than 20. I know that.
Sorry, what did you say when you're saying that when you ask for speed, you're asking for the magnitude and the direction?
Speed? No. So if you're asked just to give velocity in a problem, it means you're going to really be giving the magnitude and the direction. So if you said, what's the final velocity of the object, right, and it was moving up and down, you'd have to say either positive or negative. You'd have to give a directional for that velocity. But if I ask you for the speed, it means that I don't care about the direction or the angle. It's just the magnitude itself, just the length of that vector right there. So that's a horizontally fired problem with impact speed together. Do you see what I'm saying? How you can put these types of problems together now? So you could have another problem with the same thing, right? What if instead I said, find the velocity after 0.1 seconds have elapsed? What formula would you have used instead of this? Instead of this formula here, what formula would you have used to find VFY after 0.1 seconds have elapsed? What are you thinking, Alex?
The one with time.
Yeah, the one with time. I'd probably use this one. Now, you have the other one that involves time as well. They don't all involve time. There's no need for that comment to make. One does not involve time. So yes, this one is the better of the two that involves time, though. I would use this one because you're finding VFY, and then you're putting it back together. You could use y equals VIT plus 1 of AT squared, but what's that going to give you, honestly? It won't give you VF. Your y is already known as 15 meters, so it's not going to help you at all. So that's a formula that becomes pointless to use here. Notice, did I do anything in the x direction for this problem at all? So when is the x direction used?
When it's constant.
It was constant here.
To find x displacement.
To find the x displacement or to find time. All done. It's one of those two things. If your problem is not referring to x displacement or you don't need the time during the problem, there's a good chance that you're not going to use any formulas in the x direction. You might use the value that you have here, as we did here, but you will not necessarily use v bar x equals x over t unless you're looking for x or t. Right? One of those two things. Now remember also that there might be a problem where you have to find, for example, the height that it falls. So you might have to use y equals VIT plus 1 FAT squared. So then you would need to get t in the x and move it over. So when you're on the test, I'm going to try to be nice and step you through by giving you parts A and B. But if you have a problem that says just find the vertical displacement, maybe you need to find time as an intermediate step to get the vertical displacement. Right? It's one of our, what do we call that variable? The linking variable. It's in both directions. Okay, it's in both directions. I don't know how much time we have left, honestly. I have no idea. So we'll keep going till the bell rings. What else?
Time.
Yeah.
Go over 99 of the problem set.
I brought the book. You're lucky. I was about to say I don't have the book. Page 148.
I think so.
Yeah, this was the lob pass versus the bullet pass. Correct?
I
You understood the lob pass, it was the lower pass. Okay. So that's then part B. Part B says the bullet pass is thrown with a launch angle of 25. What's the initial speed of the pass? And then it says, what is the time of flight of the bullet pass? Okay. So here's the key, folks. The diagram gives you a lot of information. The diagram for the bullet pass looks like this. For the lob pass, it looks like this. They both have the same trajectory. By the way, what are those angles? They must be what kind of angles if they land in the same spot? We did it in the lab. Well done. Not many people picked up on that in the lab. The angles that have the same x displacement are always complementary. So if I launch at 50 degrees or 40 degrees, they have the same landing point, just different paths. If I launch at 30 or even like 10 degrees, a really low angle, it lands here. 80 degrees also lands in the same spot. Complementary angles have the same range. Good thing to know for sure.
Will that be on the test?
Anything we talk about in the test. Yeah, it was part of your lab. If you look at your lab, I actually talk about that. So, in this problem, we know that these angles are complementary because they have the same range. We're given the lower angle for the lob pass as 25 degrees. We're asked to find first the initial speed. That's what we're trying to find. We know the height of this is around 5 meters. You have to make that assumption. We know that the full length is around 35 meters. The other height was up here, around 20 meters. You could have used 19 or 4. I know it wasn't exact, so whatever you use, it really doesn't matter. But you have to assume some sort of number here. So what I would do for this kind of a problem is I would recognize I have nothing about VI at all. I have nothing about the x besides the length. I know it's 35 in length, but I don't have the time. and I don't have VI, which is two unknowns in the x direction. That's not going to help me at all. I can go to the y direction and try to use y equals VIT plus 1 half AT squared. But t is unknown again, and so is VI, so I can't use that one, right? There's one formula I can use, though, that doesn't involve time. What's the formula that doesn't involve time that we can use in the y direction in this case?
Bf to the second plus bi to the second equals, plus 2ax, sorry.
That's all right. Now, the only reason we would use this problem, you might say to me right now, well, we don't know the final velocity, Mr. Howell, and you're right, we don't. But what's the velocity in the y when it reaches max height? And don't we know the max height? What's the max height? What is it?
5.
It's 5, right? So we could say this.
To the max height, VF is 0.
The max height is 5 here, and when you reach max height, your velocity in the y direction is always 0 in the y direction. Now, don't we know theta? Wasn't that given in the problem? It was 25 degrees. So let's just fill in for theta here, and we can solve this problem. Okay, that's the way you would solve a problem like this. That's the easiest way to go through this part. Again, your goal is to find VI, not VIY. This is VIY squared, but VIY is VI sine theta. So we have to remember that V bar x and VIY have definitions. One is, again, in the x is VI cosine theta, and in the y, it's VI sine theta. Solve that equation for VI, and that's how you get your initial velocity, using only what we were given. I don't want to have to find time. I couldn't find time here. It's not enough. If I did, what would I have to do if I have both VI unknown and time unknown? What do I have to solve? What do I solve if I have two unknowns?
Quadratic or
Substitution.
Yeah, a system. A system involves a quadratic for sure, and we use substitution, correct. But I solve a system if I have two unknowns, like the salmon problem. Recall the salmon problem, number 4, example 4 from class. We had two unknowns in that problem. Both VI and time were unknown.
Yeah, substitution.
Yeah, I did it the other way because I set y equal to 0.
You should be able to do a substitution problem. Would it be as lengthy as the salmon one? Probably not as lengthy, but you should recognize that, hey, if you have two unknowns and two equations, you should be able to substitute them into each other. Absolutely be able to.
So is this like
Part B.
You get the same answer, like 20.
Because I assumed the problem ended at max height for this. I did the max height, I turned it into a max height problem.
That's what I
What was the max height? Was it 5? So if I use 5 here, I'm at max height. If I use 0 here, I'm at the ground at the end.
I don't think
because I did it like
Depends on what I plug in here. I think it's like 4.9 technically, guys. It's right below the 5 mark. You can see it.
So we can assume that?
Why else would you be given a graph? Right? I mean, it literally says there that that figure responds to curve 1 and curve 2 respectively. Yeah, you have to use the graph to do it.
Wait, can you do it the substitution?
Yeah,
way?
you can. Yeah, absolutely. It's just a lot more work than it's worth. It's a lot more work. Steve, how much time do you have? Wait, the bell rang?
107, that's 107.
Go then, go. Sorry, guys. Oh my gosh, my bad. I was waiting on the bell the whole time.
Now I'm gonna do well on this test,
Have a good day, guys.
though. Wow, these explanations are so helpful. Yeah, who's in there?
Any hard copies of problem sets? Hard copies, going once, going twice. Any late labs? There's still some late people for labs. Tomorrow is the last day to accept the lab.
No, 2. I got it.
There's 10 of them there, and they're all solved. Documents and handouts on Google. There are a lot of practice problems that are already solved to work through. Sorry, can I ask Jack? You got it? Yeah. Okay.
I'm good. Do you have any hard copies upstairs?
Yeah, get that lab in. Go to grades. Yeah. I have no hard copies, but I have to put the solution in there. Why don't you wait for the beginning of this period for this class to come in, and then you can come. Yeah, collect their labs actually for me first. Their labs you do that. So collect those, and then I can hard copies.
Alex was telling me about
And he was like, yeah, you can use range.
Oh, that's right.
Yeah, but then I was like, what is it?
Yeah,
We
they don't
didn't
know.
learn range.
Not
That's
to mention,
what-
it only works when you start it in the ground. Now, like 4 or 5 kids were using it for other problems.
Right.
It doesn't work unless you have y equals
That's
0.
why I was like,
I actually used to coach it too, so I tell them every year, like, I don't like using the range equation because you have to know that y equals 0. And a lot of kids use it when you're launching up to a cliff or launching down. So it doesn't work in those cases.
it's not range.
All right. Grab a seat, grab a seat. I want labs out on the desk. Labs are due today for you guys? Tomorrow. Thank you. Sorry. My bad. Problem sets, right? Hard copies of problem sets are due today. Those are definitely. Any hard copies? All electronic? Give it a minute, Steve, because some people are still filing in. Just make sure everybody. Sorry about that. My bad on the heart attack there. Little mini heart attack.
I was like, oh nah.
Hey, Joe. Gibson.
Nice sigh.
All right, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Who's out? Who?
DeLon.
Oh, I forgot.
Is he absent, really?
Yes.
Oh my god, you remember?
How could I forget?
Is he sick? Do we know? He was not sick yesterday. He was totally fine.
No, he grew up when we were running.
No, but everyone shows up running.
Oh, for basketball. I threw up in the middle of practice, came back in and finished practice. He'll get over that crap.
Yeah.
Oh yeah. My dad used to run us into the ground, Joe. One time I had too much pizza before basketball. My dad was the coach, and I was embarrassed. I ran, puked, came back in, and jumped.
I'm kind of tired.